Hi everybody, welcome to section 1.5. It's called Leibnitz Notation and the Sum Difference Rules. So as I mentioned in the live session, essentially what this section is, it's teaching us the shortcuts to take derivatives. So I'm actually going to write that off to the side. Let's say shortcuts for derivatives. All right, so that's what we're doing here. But let's talk first about Leibniz notation. So we saw, I'm just going to say a quick recall. When we had f prime of x, we called that the derivative. This is the derivative of the function f of x. Now, where that comes from, there's historically two different people independently, they feel, discovered calculus at around the same time. This f prime notation is what Isaac Newton used. So this is Newton's notation. And another gentleman named Leibniz in Germany around the same time discovered calculus, used different notation. And so what he did, instead of f prime of x, he called it dy dx. And it's the derivative of y with respect to x is often how we say this, but this is also the derivative. And we would usually write that as the derivative of y, but remember y and f of x are the same thing. Now, one reason we need to see this, we'll see it periodically where they use that notation, often prime notation. But the dy dx works really well when you're trying to keep track of the unit. The last live session we did the rate of change of revenue, and that was were dollars per unit. Well, the dy was the change in y, which was the revenue. So the change in revenue per unit. Okay, so it's a rate of change. Now, the other reason we need that, though, is we can think of this dy dx. What it's really doing is it's taking the derivative with respect. Well, that d dx says we are taking the derivative of y. So we're going to use this notation to say we're taking the derivative. So this means we are taking the derivative of whatever is inside that parentheses. Now remember, the dy dx up here, dy dx is the derivative. So if you have d dx, there's no y there, it's saying you're taking the derivative of something. So d dx, we're going to take the derivative. Dy dx is the derivative. So if the y is not there, we're getting ready to take the derivative. The dy dx says I did take the derivative of y. Okay, so just a little notation there because we're going to use that for the shortcuts. And in fact, I'm going to jump right in and I'm going to show you the first shortcut rule. Now, let's say shortcuts for derivatives. Now, remember, the derivative is the instantaneous rate of change. So the first one, we're going to do the derivative of a constant. So here's my first rule. We'll even title it derivative of a constant c. So if I'm taking the derivative, right, the d dx means I'm going to take the derivative of what? Some constant c. Well, think about it. The derivative is the instantaneous rate of change. by definition, a constant does not change. So at any instant, it's not changing. What that means is the derivative of any constant has to be 0. Now, again, it's the rate of change. Constants don't change. So we say, oh, there is no change in this constant. Its rate of change is 0. Another way to look at that is graphically, if we wanted to. I'm going to do it off to the side because I want this list to be nice and clean of the shortcuts. But if I've got a curve like this, and then let's say we've got a line up here, and let's make that line y equals 3. Well, the reason I'm saying y equals 3 because it's a constant. There's no variable x there, so y is always 3. It's not changing. If I go any place on that curve, say I go right here on the curve, and I say, hey, what's the rate of change? Well, remember graphically, the rate of change or the derivative is the slope of the tangent line. Well, the tangent line here is going to be the line itself. And you know what the slope of a horizontal line is? 0, because it's not going up, it's not going down. Its slope is 0. That means the derivative is 0. So graphically, it's a horizontal line, slope is 0, slope of the tangent line is 0, derivative is 0. But I think if you understand the fact that, oh, it's a constant, it doesn't change, the derivative has to be 0. So that's my first one. The derivative of a constant is always 0. All right, let's go to the next one. And this is the power rule. I'm just going to give it to you. So the power rule is going to say if I'm taking the derivative of x to some power, we'll use n as the power. And I know n is a constant there, not a variable, because that d dx, whatever's on the bottom is the variable. So if I said d dn, n would be the variable and x is a constant. But the d dx says x is a variable, meaning any other letter has to be just a constant. When I take the derivative of that, what I get is I bring that n down in front and I multiply it by that x, but then I drop the exponent by 1. And it's a weird rule, but in the live session, one of the things we just did, we were taking the derivative. Part of what we were taking the derivative was an x squared. Well, the x squared piece that once I took the derivative and I went through the limit as h goes to 0, the whole difference quotient, what I ended up with was just 2x as the derivative of that piece. The reason it's 2x is I bring that 2 down in front and then I drop it by 1. Oh, that means it's 2x to the first, or we just call it 2x. And you don't have to write all those steps down. Hopefully in your head, you will be able to say very quickly, oh, it's just 2x. So let me erase that dot up there. That wasn't what I was trying to erase. So the derivative of x squared is just 2x. Bring the 2 down, drop the exponent by 1. Works for every power. We're going to see a bunch of examples. Doesn't matter if the power is positive. Doesn't matter if the power is negative. Doesn't matter if the power is a fraction. It's still, we use that same property. And that power rule is the one biggest shortcut rule that you will use. All right, let's see a couple others. 3. Now, we've got our power rule. We've got our constant rule. Well, what about a constant multiplied by a function? So this is called the constant multiple rule. And what this is doing, I should probably just underline all these. I'm going to go back up and underline this. So now I'm taking the derivative of some constant times the function. So I'm taking the derivative of that whole thing. Well, what I can do is I keep the constant as it is. And then I just multiply by whatever the derivative of that f is, which is f prime of x.
So if the constant is all by itself, say I'm adding or subtracting a constant, that piece goes to 0. But if the constant's being multiplied by the function, I'm going to keep it and multiply it by the derivative. Here's what I mean. Let me give you a quick example. Say I've got the derivative of 3x to the 5th. When I take the derivative, that 3 stays there. And then I multiply it by whatever the derivative of x to the 5th is. Well, remember, we bring the 5 down, drop the exponent by 1, and so now we can multiply the 3 and the 5, and I get 15 x to the 4th. That's my derivative. And usually, you're not going to write out that step. You're just in your head, you're going to say, oh, 5 times 3 is 15, x to the 4th. Simple as that. So it's very quick. So if that constant's being multiplied, it stays. But if it's being added or subtracted, it goes away. And we'll see that in the next property. So this next one is called the sum difference rule, which is what they were talking about in the section, the title, sum difference rule. Now, all this says is that if you're adding two functions together or subtracting them, so it's the derivative of f of x plus or minus g of x, I just take the derivative of each one individually. So I can write it. The book writes it like this. I'm not a huge fan. It's the derivative of f of x plus or minus the derivative of g of x. But I'd rather just write it as, oh, it's f prime of x plus or minus g prime of x. Because we know that prime just means we're taking the derivative. And it looks like a weird rule, but here's where it is. Here's the example. So say I'm taking the derivative of x squared. I think this is what I had on the live session. I think this is the example I did, and I showed how to do the derivative using the difference quotient, and the limit as h goes to 0. Well, we already saw to take the derivative of x squared, we just bring the 2 down, and then it's x to the first. So we bring the 2 down, and then it's x, and we drop the exponent by 1. This doesn't look much like a 2. I don't know what that's all about. Now, with this 2x, one way to see this is that's really x to the first power, and then 2 times 1 is 2, but then the x to the 0 is just 1. The x essentially goes away. So this is really, and I'm going to write it out, although it's 2 times 1 x to the 1 minus 1. And then remember the derivative of constant 0. I just use that property, the plus or minus property, the sum difference rule, because I took the derivative of the first one, plus took the derivative of the second one, minus took the derivative of the third one. And I'm just taking the derivative of each piece individually and then adding or subtracting as appropriate. But let's see what this is. So that's x to the first. I'm just going to leave it as 2x. Now, this is plus 2x to the 0, but remember, x to the 0 is equal to 1. So that really means 2 times 1, which is just 2. The minus 0 goes away. So I just get 2x plus 2. I don't go through all those steps on that 2x to get down to the 2. What I do is I remember in my head, oh, remember the derivative is the slope. Well, if you covered up, say we didn't have that x squared there, just look at the derivative of 2x minus 9. Well, if the derivative is the slope of the tangent line, that's a line now. The slope is 2. So the derivative is just 2, which is the 2 we had over here. So if you have x, since our x is dropping down 1 degree, 1 power, if you only have x to the first power, we lose that x and it just goes away. turns into a 1 is what happens. But when you multiply by 1, it doesn't change anything. But don't make it hard. Don't have to go through a lot of steps. So if I had the derivative, for instance, of 7x, it's just 7. You just lose the x. So if it's just x to the first, since you're dropping the exponent by 1, if you only have 1x, it's just going to go away. All right, so that's the idea there. And that's actually all the properties we have, all the shortcuts. It wasn't bad. We're going to do a bunch of examples, and then I'm going to show you how to find, sorry about that. Then what I'm going to do is I'm going to, that just completely threw me off. What I'm going to do is I'm going to show you how to find the equation of a tangent line. So let's go ahead and do this. So let's do a bunch of examples from the book. So first of all, and I'm just going to make these up. We don't necessarily have to pull any from the book. So if I say, and let's say differentiate. Differentiate just means find the derivative. And so let's do our first example. F of x equals, I'll put example again here. F of x equals 6. That's a constant. Oh, the derivative of a constant is always 0. Well, there's my derivative. That didn't take long. What about, as an example, let's take the, oops, we don't want Leibnitz notation there. Let's take the derivative. Let's say g of x, we'll name it something different this time, is x to the 4th power. Oh, power rule. The derivative of that, I'm just going to bring that power down, drop the power by 1, and so I get 4x to the 3rd. And then that's my derivative. So it's very quick. Again, you can probably do that in your head. I wrote down the 4 minus 1 so you knew where the 3 came from, but obviously you can do that in your head. So that was the second rule we saw. What if I have, we'll go back to f of x. Say it's 8x minus 3. The derivative, remember, that's a line. The slope of that line is 8, or just say, oh, we lose 1x, so the x's are gone. We just get the 8, minus the derivative of constant is 0. So the answer is just 8. So as you can see, we can do the derivatives really quickly. And we want to be able to do them very quickly. All right, let's try another one. Let's say we have h of x is 3x to the 5th minus 4x squared plus 1. Well, we have to use a few properties here. We're using the sum difference rule to take the derivative each individually. We're using the power rule because I see some of those with powers. We're using the derivative of constant because I see one of those. And we're using the constant multiple rule because we have that 3 and the 5. So when I take the derivative, now showing the steps, again, you might want to skip and just go right to the answer, but the 3's constant multiple times this x to the 5th, so it's going to stay. But I bring down the 5, and I drop the 5 by 1. And I do the same with the 4. Bring down the 2, drop the exponent by 1. The 1's over here's a constant, that just goes to 0. But ideally in your head, you just thought, oh, 5 times 3 is 15, drop the exponent 1, minus 8x, done. Again, very quick. You don't have to write out the steps. I'm just writing them so that you see what the properties were in case you're saying, wait, where did the 15 come from? How come that's an x to the 4th? Whatever the case is. But we actually used all 4 of those different properties in that problem. All right. So now here's where it's going to start to get a little bit weird. What if I have, I'm going to f of x again. That's the old standby. what if I have f of x is the square root of x? Well, we didn't see how to take the derivative of the square root, but remember all those properties of exponents we saw before? We saw that the square root of x can be written as x to the 1/2 power. Remember, a fractional exponent, the denominator is always what the root is. We don't draw a 2 right there, but if there's no 2 there, if there's the radical sign without a number, we always know it's the square root. We always know it's a 2. If we want it to be the third root, we'd have to put a 3, or the fourth root would have to have a 4. But that number on the bottom of the denominator of the exponent, that's the root. Well, so f of x is really x to the 1/2. Now it's a power. Now I just use that power rule again. So the derivative, bring the exponent down in front, drop the exponent by 1. Now, we'll show that off to the side. The 1/2, that didn't look good. The 1/2 minus 1, hopefully you'll get this quickly in your head, but the idea is I need a common denominator, so we'll make that 2 over 2. So it's really 1 minus 2, which is -1, and then you keep the denominator. And you probably know that 1/2 minus 1, we flip around 1 minus 1/2 is 1/2, but it's negative because the bigger one was negative. So this is really 1/2 x to the -1/2. And you can either write the answer that way. Again, practice on the homework online to see how they want you to write the answers, because what they might do is they might do this. Now, remember that 1/2 exponent means the square root. The negative, remember, puts it down in the denominator. So I've already got the 1/2 here, but the x to the 1/2 goes to the bottom this way, but that's really the square root. So they may write the answer this way. I don't know. I think they'll often accept it as 1/2 x to the -1/2 power, but put it in and see. If not, they may want you to change it, but I think a lot of times they will accept that other answer. And that's why I give you practice problems, so you know what the computer's looking for. Okay, so fractional exponents. Let's do another one with fractional exponents so you see this. So g of x, let's say we have the third root of x to the 5th power. Now, same idea, it's still x to the 5th, but the third root just puts a 3 on the bottom. And so when I take the derivative, I bring that exponent down, 5/3, x to the 5/3 minus 1. And again, remember that minus 1 is really 3 over 3. We need a common denominator. And so 5 minus 3 is 2, and the 3 stays. So we say, oh, it's 5/3 x to the, and then 5/3 minus 3/3 is 2/3. That's my answer. Again, if you want to put it back in radical notation, there's no negative exponent, so it stays on the top this time, but it's the third root of x squared. And then this 3 is on the bottom. Again, I don't know on the homework which one they're going to accept as the answer, but you should understand that it can be written either way. Okay, and we talked about the negative exponents. Let's look at a negative exponent. So let's say, for example, 1 over x to the 4th power. How do I do that? Well, I change it to x to the -4 power. Remember, a negative exponent would mean a fraction. And then I take the derivative just as I always do with the power rule. Oh, it's -4 x to the -4 minus 1, or -4 x to the -5. If I want to get rid of the negative exponent, I have to move it to the bottom, but that -5 is just related to the x, so the answer would be -4 over x to the 5th power. It's only the x to the 5 that goes to the bottom, not the negative 4. The negative 4 doesn't make the 4 go to the bottom. It's only exponents that are negative that make it go to the bottom. All right. And if I look in the book, well, here's one that I've seen would confuse students sometimes. Let's do this one. It's going to have 2 pieces to it. Example, let's call it k of x. And I'm going to do a couple things. One, I'll do 4 over 7x to the 3rd. And let's just say minus x, because I want to make sure that you know how to take the derivative of just x. Well, think this way, that 4/7, keep it as 4/7, but then x to the negative 3. And then we'll just keep that negative x out here. I can't combine those at all because they're not like terms, but when I take the derivative k prime of x, again, 4/7 stays because it's a constant multiple, bring down the negative 3, and then x to the negative 3 minus 1. The derivative of this x, remember that's a 1x, so the x goes away, we still have a 1. Because if that was a line, it'd be a line with slope 1. And so to clean this up, it's just negative, now I can multiply the 3 and the 4, negative 12/7 x to the negative 4 minus 1. I'm going to leave it that way. Again, if you wanted to move the x to the 4 on the bottom, it's negative 12 over 7x to the 4th minus 1. It could be written in either of those 2 ways. We'll put another equals right there. But a lot of times people will want to move that 7x to the 3rd up as a negative 3. The 7 stays because the 3 doesn't affect it. It's not attached to that. All right. But here's what I want to show you. In the last section, they had some problems where they would ask you to find the equation of a tangent line. I didn't want to do it in the midst of finding the derivative the long way with the limit of the difference quotient. So now that we have the shortcuts, we can do that. So let's do a couple things. One's going to be this. Let's say this. Find all x values where the slope of the tangent line is horizontal. Now think what that means. Say I've got a curve that looks like this. It's a parabola. The only point where the tangent line is horizontal is going to be right down here, right at the bottom, right at the vertex. A horizontal line has a slope of 0. What's important about that? What does that have to do with the slope of the tangent line? Well, remember the slope of the tangent line is the derivative. So when they say slope of the tangent line, that's just the derivative. Well, if the slope of the tangent line is horizontal, that means it's equal to 0. That means the derivative is equal to 0. So what we're going to do is we're going to find f prime. We're going to set it equal to 0, and we're going to solve it. That sentence, find all x values, I should have put an S there. Find all x values where the slope of the tangent line is horizontal could be rewritten to say, find all x values where the derivative equals 0. They don't write it that way because they want you to understand that's what it means. Okay, so let's go from there, and we're going to do one of these. So the function I'm going to give us, we'll just make it up, 3x squared minus 4x plus 5. So I take the derivative, f prime of x, well, remember, bring the power down. So it's 3 times 2x to the 1st minus, that x goes away, 4, and then plus 0. So the derivative is just 6x minus 4. So I just set that equal to 0. So I say, oh, 6x minus 4 equals 0, and I have a nice linear equation to solve. Add 4 to both sides. 6x equals 4. Divide by 6. I'm going to reduce that to 2/3. That's the only x value on the curve where the tangent line is horizontal. What I actually found right there was the vertex, at least the x value, the vertex of that parabola. And if you remember with parabolas, you could find the vertex by doing negative b over 2a. If I do negative b over 2a, well, b is going to be positive 4 over 2 times 3 is 6. I get 4 over 6. Oh yeah, I get 4 over 6, 2/3. So that was, this is actually the x value of that vertex. The good part about calculus is if I've got a parabola, I could find the vertex before. We had other ways of doing it. But say I have an x cubed that looks like this. The tangent line is horizontal there and also right here. So I can find tops and bottoms of any function that's differentiable by just setting the derivative equal to 0. And that's where we're going with this. We want to use calculus to find several things, one of them being any maximum or minimum values on the function. Okay, let me close that back down. Here's the next idea, though. What if the problem says, find the equation of a tangent line? And we'll just make this one up. So let's say we have example, find equation of tangent line of f of x equals, what do we want here? Let's just say it is how about 5 over x to the, we'll just do x squared at, and let's say it's at the point, we'll make the point relatively easy, 1, 5. You notice if I plug in 1 for x, I do get 5 as my answer. So let's find the equation of the tangent line there. Now I will tell you, this is kind of a weird graph. This graph looks like this. That's what this graph looks like. So what I'm doing is I'm finding the tangent line over here at 1, 5. I don't know where, maybe it's about here. I don't know. So the tangent line should look something like this. We'll see what it is. So let's see. So what do I do? Well, let's change f of x to 5x to the negative 2 so that I can take the derivative. And why am I taking the derivative? Well, because the derivative is the slope of the tangent line. Well, that derivative, 5 times negative 2x to the negative 2 minus 1, or negative 10x to the negative 3. That's my equation for the slope. So I say, okay, now I've got an x value where here's my x value right there is 1. I'm going to plug that 1 in right here. Now notice this is negative 10 over x to the 3rd. We'll just call that f prime. Again, we know that's the slope. I'm going to plug in the 1. So f prime of 1 is negative 10 over 1 to the 3rd, which is negative 10 over 1, which is just negative 10. That's the slope of that blue line. So apparently, it would have been better had I put the line more like here, because it's got a really big slope. It's a really sharp negative slope there. So now I have the slope. Well, let's find the equation of a line. And you may have done point slope form, y minus y1 equals m times x minus x1. I'm not a huge fan. I'm just going to use y equals mx plus b. And the reason is I already know m, I just found it. All I need to do is find b. And what I do, they gave me a point xy, I'm just going to plug those in. So I'm going to do it this way, y equals mx plus b. We just found that m was negative 10. They gave us the point up here, 1, 5. The 1 is the x, the 5 is the y. I just plug those in. So the y was 5. The slope we just found to be negative 10. The x was 1, and I'm trying to find b. And so I say, oh, 5 equals negative 10 plus b. And then we just add the 10 to both sides. We get 15 equals b. I take that 15 and I plug it in there. I already knew the slope. That goes there. So my function is y equals negative 10x plus 15. Done. That's the equation of that tangent line. And so it goes pretty quickly. I don't, since this is recorded, I don't need to go through a lot of examples. And so I'm not going to. I gave you one example of what to do to find when the tangent line is horizontal, just means the derivative is equal to 0. And we did an example of finding the equation of a tangent line. I do like especially the idea of finding the equation of a tangent line. So do be prepared to see at least one of those on your first test. And by one of those, I mean either the x values where the tangent line is horizontal or the equation of the tangent line. I wouldn't give you 2 equation of tangent line problems, but I may give you one of each of those types of problems, or just pick one of the 2. But do be prepared for that. If you see questions like it on the practice problems, you may see problems like it on the exam as well. All right, that is as far as I was going to go today. So I'm just going to leave that there. Practice this stuff, just the one section today. So hopefully that makes sense to you. And if there's anything that's confusing you, just go ahead and ask me during the live session, and then we'll talk more about it then. All right, have a great day, and I will talk to you soon.